Let's begin with a simple definition. What is calorimetry? Calorimetry is the experimental process of measuring energy changes in a system using an insulated container and a thermometer. When using a calorimeter, we rely on one main principle. In an isolated system, the energy lost by one substance must equal the energy gained by another. In the real world, this is not possible as the calorimeter is not a perfect insulator, and energy is lost to the surroundings. In order to make caloremic calculations, we must make a few assumptions. Number 1. No energy is transferred between the calorimeter and its surroundings. Even though we know this isn't true, this assumption is necessary to simplify calculations and provide experimental data. Number 2. Any dilute aqueous solution used in the calorimeter is assumed to have the same density and heat capacity as water. This is because the solute is insignificant compared to the amount of water present in the solution, thereby making very little difference to the specific heat capacity. Since these assumptions are being made, the answer will not be 100% precise. There are several calorimeter designs, but they all follow the same general outline. They contain insulation, thermometer, and water. The temperature of the water is measured before and after the substance is added. This data is used for several calculations. There are two types of calorimetry problems. Case 1 for non-reacting processes, and Case 2 for reacting and dissolving processes. In this lesson, we'll be focusing on Case 2. In Case 2 problems, parts of the system undergo either a chemical reaction or dissolve, effectively causing them to disappear. To find the energy gained or lost by water, we can use the equation Q equals mc delta T. This is because we can measure the mass and temperature of the water. Additionally, we know the specific heat capacity of the water as well as the solution due to the assumption we made earlier. To find the energy gained or lost by the substance, we cannot use the same equation as the substance disappears, either via chemical reaction or dissolving. Therefore, to find the change in energy, we use the equation delta H equals N delta Hx. This is because the number of moles of the substance remains constant. Since we know that the energy lost will equal the energy gained, we know that negative delta H equals Q. From this, we can get our final equation of negative N delta Hx equals mc delta T. When solving these problems, we identify the given variables and solve for the unknown. Consider this example. A 0.5 mole sample of a solid ionic compound was dissolved into 35 grams of water, causing a temperature increase of 15 degrees Celsius. What was the molar enthalpy of the solution? We begin by writing down all the variables that we know. 0.5 moles for the compound, and we do not know the delta H solution. For the water, we know that the mass is 35 grams, the change in temperature is 15 degrees Celsius, and the specific heat capacity is 4.184 joules per gram degrees Celsius. This is a constant. We can then write the equation that we know and then solve. We substitute in all the variables that we know. Using algebra, we find that the answer for delta H solution is equal to 4,393.2 joules per mole. For significant digits, we reduce this down to 4.39 times 10 to the power of 3 joules per mole. Finally, since delta H is supposed to be in kilojoules, we convert it one more time to 4.39 kilojoules per mole. This is our final answer. These are some common errors that students make when solving these problems. Number 1, remember to apply significant digits. This is important for full marks. Number 2, the delta Hx is in kilojoules per mole, whereas the C is in joules per gram degrees Celsius. You must keep this in mind when doing conversions to make sure the units for all measurements match. Divide the C by 1,000 or multiply the delta Hx by 1,000 to keep the units consistent. If the substance is given, then the delta Hx can be found in a reference table. That would be given. Remember, the negative sign needs to be on one of the sides. This is because exothermic reactions are negative and endothermic reactions are positive. Consider the second example. 15 grams of a substance was dissolved in a calorimeter. It caused a temperature change of 23 degrees Celsius. The calorimeter was calibrated and the heat capacity is 575 joules per gram degrees Celsius. What amount of energy was involved? Sometimes heat capacity is given instead of specific heat capacity. This is when the efficiency of the calorimeter is known and is incorporated into the calculation. Thus, we use a new equation, Q equals C delta T. We plug in our values and we solve. Our answer turns out to be 13,225 joules. Accounting for significant digits, we get 1.32 times 10 to the power of 4. This is a simpler problem, but it outlines the point of calibrated calorimetry. The mass is irrelevant because it was calibrated. Remember to look for this word when identifying these problems. This concludes the lesson on calorimetry. Thanks for watching.